Thank you, Dr. Sangupta. It is my pleasure to be sharing some of our work. So, uh, uh, Geospatial and Remote Sensing Research Laboratory that we have here in Department of Earth and Atmospheric Sciences. We use remote sensing for many applications, and some of our research related to critical minerals. I'll be sharing some of those results. It's mainly part of chapters from dissertations of my former students or some current students, and um, publish in several peer-reviewed papers, and is funded by several federal agencies. We are also thankful to some of the mining companies like MP Materials for rare earth, Kennecott for copper, Liberty Gold for allowing us to access their mines. Navajo Energy Transition is another coal company. And also Parish Power Plant provided us some of the samples. So I'll just be sharing some of those results with you. To start with, what are critical minerals? There was this report by NRC in 2008 that talked about critical minerals. Today we hear about critical minerals from everyone, from White House, from Congress, from USGS, from other government agencies, academia. Everybody is talking about critical minerals. But what are critical minerals? New York Times in 2010, and there were several other media, they reported that Japan was facing some kind of threats that rare earths and critical minerals supply would be stopped to them. And that kind of alarmed many people. And you may have heard similar kind of news a few years ago. So critical minerals are elements and minerals. Those are important for economic reasons and are critical for carbon net zero technology or modern machines, electronics, or batteries and magnets. It's really important for those. So USGS and US government, they put together this list and added 10 new critical minerals that were added last year in November. So there are total 60 such elements or minerals. In addition to that, White House action put gold of significant importance and put it with critical minerals. So these are important. And the main thing is that if there is disruption for supply of these elements, this could create serious problems. So therefore, they are put as critical minerals. So as geologists, although this critical terms is new, as a geologist, we are working on minerals. Geologists are working for centuries on economic minerals, and many of them are now considered as critical. And if you look at this distribution of critical minerals globally, we have some specific areas where we have a lot more critical minerals. This area in blue, the Western United States and Western Americas, those are subduction zones. And then we have all this region in Alps, and then here in Himalayas, as well as this Ring of Fire. Those are places for substantial copper deposits, the largest copper deposit in this region. Then we have this cratonic area, old rocks, with rare earth, lithium, and nickel and other deposits. And then we have this blue areas, and green areas here, that's the rift zones. Today, the largest reserves of rare earths are in China. Nickel is in Indonesia. And cobalt is usually a co-product or byproduct of nickel and copper that is in Congo. Chile has lithium, larger deposit, and then copper again, Chile and Peru. So the spatial and secular distribution of critical minerals, or mineral deposits, is well described by global plate tectonics. So these are the three end members that I'm showing. This area is the subduction related area that I showed in the previous map, the blue area. So here we have this subducting plate that releases fluids. Those fluids cause melting in mantle and then create this zone of melting, assimilation, storage, and homogenization. In this area, we usually have these cumulates, which could be economic. And then over time, this magma rises and create this magma reservoir in crust, upper parts of the crust. This is the area where we have pegmatite deposit from like lithium, rare earth, and other pegmatite-based critical minerals. Even further upward in upper crust, plutons are found, which are again important for copper, rare earths, and other deposits. And some of these shallow intrusions in hydrothermal generates what we call as porphyry copper, which is the largest deposits of copper. And then we have at the surface, some of these already existing deposits are reworked, and weathering and groundwater processes rework those and make deposits. And then this is this subduction zone. Then in the rifted areas or the extensional regions, specifically, we have this decompressional melting of mantle and fluid rise. And there is a specific type of fluid that forms carbonatite pluton. That is the best source of rare earth elements. And then even further in intraplate settings, we have hotspots, whereas the source of magma is very deep. When it comes, it makes this large layered complexes like mafic ultramafic complexes, which are source for platinum group elements, chromium, and other elements. So broadly, there could be three categories of critical mineral deposits. Magmatic, the source for whether it's carbonatite or pegmatites, those magmatic sources. Then we have hydrothermal deposits, which is the hot water and associated mostly with the magmas. And then we have the surface processes that concentrating some of the elements. So with this introduction, you can see that minerals are located in different depths, different locations. So there are many exploration techniques that has been over the decades and centuries being developed. So geological exploration usually involves mostly surface observations, remote sensing, which advanced a lot over several last years. That is the main tool that we use. Again, it is mostly focused on surface deposits. And then there are the geochemical and geobotanical techniques. That's also primarily surface. They looked at minerals surface, although this could be used in shallow subsurface also. Geophysical techniques are used for imaging subsurface for mineral deposits. And finally, drilling is done and further analysis is done to develop a target for any of the mineral deposits. There is with this increase in data analytics, now there is increased efforts to integrate all these data sets in a better way for exploration of minerals. So USGS has in 2009 initiated this efforts that's called Earth MRI. They're collecting geophysical data, aeromagnetic, gravity, radiometric data in Western United States, Alaska, and many other locations. They're also supplementing that with hyperspectral imaging that we most of the time work on, and LiDAR data. So that is being happening, and more data is becoming available. So let's talk about what we are working on and what I will be sharing with you results for some of our projects from last 5 to 10 years. I'll be primarily sharing with you results of hyperspectral imaging. Hyperspectral, you see this image cube. This is a example of hyperspectral data. There are these are special type of rock. We call it ophiolite with chromite deposits. We have those. And then what you see at the bottom, this is stacked of different bands, wavelengths. So that is this. There are sensors now in satellite base In the past, there were very few, but I think in the last 5 or 10 years, 5 or 6 years, there are several satellite-based sensors that's available. We obtained these hyperspectral camera through funding from NSF. So the idea is, as a geologist, the best place for us is vertical outcrops or mined. So this is an example of what hyperspectral imaging could do. These are two cameras. We scan the outcrop. This is a mine face. It's a gold mine. And we image this, what you see here, this gray colored rocks. We could create then maps of minerals and elements. So these colors are showing these different minerals and different elements. So you could create something like that. You could find association of economic mineral, or you could find even the processes by which minerals are concentrated. So how it is done, we have this different, like this cube, we have just different bands stacked together. So these bands, every band, if you pick one pixel in it, it has some reflection and some absorption. That is unique for some materials and minerals. It creates this kind of curve, spectral response curve. That curve could be unique, and using that, different minerals could be mapped and identified. And we have these cameras in laboratory setting where we could image these rock samples or mineral samples to micron level. And we have the spectroradiometer where we could image even at smaller size samples. And then we have a new camera that we could put it on drone, hyperspectral camera, and we could image larger areas. And normally we analyze and rock samples or confirm our results by geochemical techniques. Here are the example of XRF and LIBS, but we use ICP, MS, and other techniques, electron microscopy and other techniques. So in this next half an hour or so, I will be showing you some example. The first example is for our project in where we use multispectral remote sensing. It was conducted maybe 8-10 years ago. So we didn't have lots of hyperspectral data, but it's for gold exploration. Then I'll show you example of imaging mine faces in gold mine, and then Bingham Canyon copper mine, the largest copper mine. I will be showing you some of the data from there. And then finally, I'll be showing you our work from Mountain Pass, where we worked on rare earth elements, and then our current work that we are working on coal fly ash. So it is in many parts of the world, you'll find that in rivers, people pan the sediments of river, and they could either find specks of gold or fine grain gold that could be concentrated. So, for example, here there's panning it, and then finally this is a gold that's removed from these sediments. This is very common, and this is also common in Himalayas and northern areas of Pakistan. This means that there is gold in the source rock, but I think, is there a deposit or not? That is always a question. So this was the project we conducted a few years back. So just a little bit background. Would you see this red line? South of this is Indian plate. And then this area in between is Kohistan Island Arc or Paleoarc. And then we have Ladakh here. And then this northern area, that's called Karakoram Block. That's Eurasian. That's the so these were the two continents. And in between, we have this island arc sandwich. So these samples were collected all along the rivers, and they were stream sediments were analyzed by Geological Survey. And they indicated that there were some areas here in the purple that has higher concentration of gold. But although this is a big magmatic complex, this is not a big mineral deposit that's been discovered. There are small local mines, but not a big one, especially for gold. So there are, like, for thousands of years, people are getting this gold specks in the Indus River and other rivers, but there is no real deposit of gold that's been discovered. So the idea was to look for the source rock of gold in this region. So we started with remote sensing, and we have this example. Here you could see this location where we have the analyzed gold that's indicating anomaly of gold, there's the presence of gold. And then we looked at the host rocks in that region. So we had this kind of alterations. This is copper mineralization, um, malachite, and then we have limonite, and we have these kind of alteration product. So we targeted these alteration zones, and we picked along the major river. This is one river valley, and then this is Indus River Valley. So all along that, we collected hundreds of samples, and we analyzed those for gold. And then most of the areas, we had gold, but like I think it was like 1 ppm or less than that. That's usually not economic. There was only one location right here where we had a higher amount of gold, like 96 ppm or so. So this cyan color, this shows glaciers. So really rough area right here is K2. That's one of the second highest peak of the world. So we used remote sensing. It was mainly multispectral remote sensing, and we were able to identify some of the major locations of types of rocks like batholith, um, volcanic sediments, but we couldn't specifically identify any of the minerals. Gold specifically does not have any specific spectral response, but associated minerals has. So, but lab analysis for some of those samples shows up to 96 ppm. So we worked more on samples that we obtained from the area where the gold anomaly was found. So the area like this, with chalcopyrite and copper mineralization, and then here, this thin vein, this is mainly quartz vein, with this gray color, that's galena. This is the area where we find this very high concentration of gold. 96 mean like 96 gram per ton. So that's usually very economic. We looked at those samples and we tried to find uh, associations. This is chalcopyrite and it's surrounded by the filtration zone of limonite. And here is this galena, lead sulfide, and some of those areas had the gold deposit. So gold concentration. So we, as a start for those samples, we collected spectra. These spectras are usually used to train our models, especially for hyperspectral data. So here's the example. And actually, I will show pictures of my graduate students who work on this work. So there will be several examples, and I think I'll have a student picture there. So this is one sample, how it will look like in true colors. This is 6 samples, this three. And these are this is hyperspectral data, and we classify that data. So this is the spectral angle mapper technique. Here is the support vector machine algorithm that we applied. And we did find some kind of association, especially with this sample. Right here, we had the galena, and where the alteration zone was, we would find association of gold in those areas. To confirm them, we use this scan, which is a quantitative evaluation of mineral through electron microscope, scanning. And these zones, some of those zones had the gold concentration. So further, we did some isotopic work also, but in summary, what we found, this gold mineralization specifically was associated with galena, lead sulfide, and with some chalcopyrite also. So, and most of these veins were hydrothermal, but they were small veins. That was extremely difficult to detect from satellite-based remote sensing, given most of these outcrops are vertical. Most of the area is covered usually with snow and clouds. And given that at that time, when we conducted this study, we didn't have many hyperspectral sensors. We're going to be looking at it again, revisiting that again. So now let me give you an example of gold strike where we could use hyperspectral, and that's located in Utah, southwest Utah, near the border of Nevada. There is a mining district called Gold Strike Mining District. This is part of Carlin type gold deposit which is largest in the world. Carlin type gold deposit is basically sediment hosted gold deposit, and usually gold is very fine grain, like micron in size, and it's disseminated. So in this region, this whole region, tens of millions of ounces of gold is mined and reserves are still there. So this gold strike mining district, we did some imaging, hyperspectral imaging, and tried to find association of gold and how we could use hyperspectral imaging for better mining in this region. In this area, uh, what happened, there are these carbonate rocks. Those carbonate rocks are later altered by hydrothermal fluids. So we have this decalcification, like dissolution of carbonate rock, and replaced by silica. So silification took place. And this is the time when gold, in this hydrothermal fluids, gold came and it was concentrated with pyrites, arsenopyrite. And then after the gold mineralization, also we had this quartz veining and then gypsum deposition and calcite veining. So like any of our studies, we start with the spectral data collection. So we collected spectral data, and then we, based on that, we classified different outcrops. So this is an example of one of the gold mine. Here on this left side, we have Paleozoic rocks, and then here are Eocene rocks. So this is a thrust fault. There is a faulted contact here, and most of the gold is in this zone. So what we did, we created these maps using the hyperspectral scan. So we have this carbonate depth. It shows the concentration of carbonate, and then it also shows aluminum hydroxide is a proxy for clay minerals, iron oxide depth for ferric iron, and this area, this region where we see this green area, this is the area where we have the clay minerals and some iron oxide where the gold was concentrated and fault provided impervious barrier for the fluid flow. And we use this remote sensing, as I could show you here. This is like we could use this depths of these different minerals. So it could create like a log, like starting from here to here, we could see where the carbonate is, and then we could see it which areas has clay more clay. So this is the support vector machine classified same outcrop, and this is the spectral feature fitting technique that was applied, and this is the zone of gold mineralization. Another outcrop in the gold strike, this is Covington mine, and we created again similar kind of the idea here is to find association of gold. So here we carried out chemical geochemistry also. So the geochemical data, and then combining it with clays, jarosite like iron oxide, and carbonates, we could find the areas mostly rich with gold. Higher amount of gold was the areas where we had clay minerals and jarosite. Those are the areas with gold concentration. We also there were cores which were collected in this area. We scanned those cores. So it is the example of data from cores. What you see here, this red and yellow would show higher amount of calcite. Blue would show, and green would show less amount of calcite. So we did this for calcite, clay minerals, iron, and then we also analyzed gold in these core samples. So dark brown shows higher concentration of gold, and yellow color shows low concentration of gold. So we had these patches. These patches are actually areas with low carbonate and higher clays. And then there was this part we had low permeability and porosity, and we were able to find the stratigraphic control. Just below this equator, we have higher concentration of gold. So this is like where we have the low permeability, so the fluids would stop and we have more gold concentration. So we found that most of this gold was associated with clays, and wherever we had the iron oxide, and less carbonate, and then again permeability control where it was. So moving on, this is the Bingham copper gold molybdenum mine. That is the largest human excavation on Earth. This is like 4 kilometers wide and 1.2 kilometers deep. This started in 1906, and I think over 19 million tons of copper is produced from this mine. This is a porphyry type of copper deposit, and porphyry copper deposits are the largest one, and most of the copper is in this porphyry type, but they have this systematic pattern of alteration. So if you can look at the ore, there are these different zones of alterations. We have the earlier zones like porphyritic, and then we have potassic, and then we have this ore, and then we have this phyllic and argillic zones. All those makes like halos of this alteration pattern. And then there are this systematic mineralogy in these different halos, and many of those minerals in those halos have characteristic absorption feature that could be used for identification. And that's exactly what we did. We collected data at different levels of the mine. We went all the way to the bottom of this mine, and we scanned different outcrops. So this is the spectral response of different minerals here. Let me show you some of the results. So just two or three examples what this imaging could show us. So this is the true color image, hyperspectral, how it would look like. This is we use spectral feature fitting technique, and here we classify this outcrop into different rocks. The host rock in this area is latite, quartz latite, and latite porphyry. So we could see those, and then some metamorphic rocks, and we have quartzite. And then here, the support vector machine, by that we could map this outcrop for different minerals. For example, in red here we see amphiboles, and then this purple color shows biotite, green is chloride. And when we look at this mineralogy and compare this falls in this phyllic zone of the porphyry deposits. This is another site in the mine, and here we looked at it, and here we could see biotite, and we could see illite, and we have this some garnet and carbonate. When we put it, it is the potassic zone just below the ore shell. So this is even closer to the main ore body. This is another one. So here, this is the true color image. This is the types of rock, quartzite, hornfels, and then skarns. And then here we have the mineralogy of this: chloride, epidote, actinolite, different types of amphiboles, muscovite, and micas. This falls in porphyritic zones. So different zones of this mine could be mapped by just imaging, and this could help mining and knowing where the ore is. And similarly, in the gold strike mine, it was this imaging provided us a way of finding association between different minerals with gold, and then the stratigraphic control also. So this was about gold. Now let's talk about rare earth. That's more talked about within critical minerals. Critical minerals are more talked about. It is really important because they are used in batteries, they are used in magnets and storage devices. And they are very important, strategically important among all critical minerals. There are limited locations where we have rare earth elements. One of the major type of rock that has rare earth is called carbonatite. It's an igneous carbonate rock. It's very rare. I think all over the world, maybe there are like 400 to 500 locations where we have carbonatite. That is the main primary rare earth source. Then there are these other sources like alkaline igneous rocks. We have that deposit like in Greenland. There are many other locations. And then we have granitic type of rock like S-type and A-type granites. And surprisingly, here in Texas, we have Beringer Hill, Texas, where we had one of the oldest and biggest rare earth mine in the like in 1903 till 1915. This mine was active. It's in the hill country. Currently, that mine is covered by water. That is Lake Buchanan. If you know Lake Buchanan, that is where that mine was. But because it was specifically at that time, it was mined for yttrium, and it was used as a source for light and bulbs. But then there was other cheaper sources available, so the mine was not active. And then finally, now it is covered by 100 feet or more of water. So that we have also. So these are the primary type of rare earth deposit. And then there are the secondary deposits where we have clay absorbed, iron absorbed clay deposits. We have placer deposit. We have also coal. Some of the coals are being considered as a source of rare earth elements. So remote sensing for rare earth elements. Rare earth elements, even in parts per million, are economically important. So can we use remote sensing for that? The answer to this is yes, of course, and I will demonstrate to you that we could image rare earth and detect rare earth at a close range in a laboratory setting, few centimeters from us, to several feet away from geologic outcrop. We could see it through drones, we could see it through airborne hyperspectral sensor, and even from satellite we could see it. Why? For almost 100 years or more, people know that there is a characteristic absorption features that are very specific in neodymium that could be used to detect rare earth using remote sensing. So this one studies, Raman et al. Used several samples from carbonatites in North America and suggested that it could be detected up to 300 ppm of neodymium, trivalent neodymium in samples could be detected remotely. Later, using sample from Bayan Obo, which is the largest deposit of carbonatite these times. It's in China. And then from Greenland, and they suggested these features that you see, these dips, 3 or 4 dips, these are deeper when you have more rare earth. So this shallow, when you have less rare earth, when it's deeper, it's more rare earth elements. So that is the basis of my former student, Otto Gadia's PhD dissertation. And he came up with this index we named it Bestnesite Index to map rare earth using remote sensing. Bestnesite is the name of mineral which usually have a lot of rare earth. So these are the absorption and reflecting feature that we used and for imaging. So how we started by borrowing 3 samples from American Museum of Natural History, and then we analyzed that in the lab extensively. So this green area has low rare earth elements that is shown here in green, and then the red is high in rare earth elements. And we have this deeper dips. So the idea here was to establish some kind of empirical relationship between this depth and then we carried out this geochemistry analysis, geochemical analysis using ICPs. So we came up with this Bestnesite index, and we put the scale and we put a threshold where we could detect rare earth, and where we cannot is below detection limit. So we published this paper, and then afterward, MP Material, which operates Mountain Pass, the only rare earth mine in the United States, which used to be one of the biggest one in 60s and 80s in the world, they were kind enough to provide us 11 samples, and we use those samples. Here you see is the point spectroscopy of those samples, and here we image them using our hyperspectral camera. All of those, as you could see, most of them, they could have this absorption feature, this 4 absorption feature we had. So we worked more on it. And there are some other elements also, some other absorption feature like iron, like barite, hydroxyl. They have also some of the features which we could separate. So here is the results. What we did, we use our index that we developed originally, and we fine-tune it, and we created now 2 additional indices. So it could be used as a 3-tier process for mapping the errors. So this is those original 11 samples. These are the powdered, those samples powder. And these are the 3 indices. This is index 1, 2, and 3. And these 4 samples, this sample 3, 4, this 7, 9, and 10, they all show higher Western index values, meaning they should have higher rare earth elements. And the powders of these homogenize everything. Actually, will not increase, but I think homogenize. That's what two observations from those are. When we analyze those data using ICP-EMS, we see those 4 samples are at the top of, so those with the higher Western index are showing highest rare earth elements also. So we requested MP material to allow us their mine, and they were kind enough to allow us. So here we are in the mine. What we used here, we use over drones. This is for LiDAR data. And then this is the drone with the hyperspectral camera. And this is that mountain pass mine. This is the original outcrop where the rare earth was discovered. It's called birthday outcrop of carbonatite, which was the source of rare earth and then later mining. So we scanned that one also. And then we did a laboratory spectroscopy, and this is the image of the mine. So here is that geologic outcrop. Here is the host rock cyanide, and this is carbonatite. Carbonatite is the rock which hosts rare earth. And here we have shunkonite and cyanide. When we image this, we have these different images, and here are the results of when we apply the Bestnaside index that we developed. So these red areas, they're showing higher rare earth elements, and others are areas with low or no rare earth. This is the mine. There are different types of ore, specifically this one, white color. This is the best ore, up to 12% or so of ore in that. And when we image this, we created this data. This is the Bestnaside index applied to those images. It just brightens up in the area where we have the ore. To confirm, we took samples. So what you have here, this is the true color images, and this is the images with Bestnaside. This is the ore, that white ore, the top ore, and you can see this red and yellow color showing high amount of rare earth elements. This is another ore, it's called black carbonatite, which is also considered as ore. And then these two are from the mine samples, and these are from the outcrop. So you have the cyanide, you have the carbonatite at the contact, and we have carbonatite, actual carbonatite, and this is shunkonite. In the bottom, you could see this has the highest rare earth content. And we confirmed this with the geochemistry data also. So that was very, very useful. So this is good that we could see it in the laboratory, rare earth, we could detect it. Now we tried this from a drone and from geologic outcrop. The question is, and the power would be, what if we could detect this rare earth from satellite, from space, or from airborne sensors? Then it could be dramatic. Finding rare earths remotely and finding at least the zones of those could be amazing. So there were some airborne sensors, hyperspectral, that were available. That's like Everest Next Generation, and Everest Classic was from 1986 that was available. And then there was this one Hyperion, which was experimental, a lot of noise. The satellite was available from 2000, stopped working in 2017. But then in 2019, there were several new satellites based hyperspectral introduced. This is Hisui, that's Japanese. DISUS, which is a German system sensor. Then NMAP, again, German. Prisma, this is an Italian. And then EMIT is US, which is 60. So this 60 means it's 60-meter resolution. These are 30-meter resolution. And then the airborne are 3 meter to 4. And then this is 15 meter. So these are when they were launched. And this is their spectral wavelength. We tried all of those Bestnaside index using, and we targeted this mountain pass, which is because we already know now that there is rare earth elements. This is a mine, and we could confirm it from the samples and from the field. So these are the true color images using these different sensors. This is the airborne Everest Next Generation, Everest Classic. Then we have Hisui, we have DISUS, NMAP, Hyperion. They are not taken at the same time. Most of these images were like from 2019 to 2022, but this Hyperion was much older. The mine was much different than what we have it here. And then Prisma, and then EMIT is the one with lowest spatial resolution, that is 60. Now, this is Bestnaside Index 1 for all of this. This is Bestnaside Index 2. and this is best inside index 3. All of those shows the different parts of the mine, processing area, actual mine and tailing brightens up and it could be detected in all of those sensors. Exception is this emit, which is 60-meter resolution. We do see some anomaly, but it is not as clear. So we could say that we could detect rare earth element from space up to 30-meter resolution, using 30-meter resolution. So we are still continuing working on it. Kathleen is my current PhD student. She's working on it. And what we are trying to find out the minimum limit. What would be the minimum detection limit we could detect? So here is, we are taking different parts of the sample. These are tailing samples. And we are seeing the different analysis. This is the Western side index, and this is the analysis of different part. So far, the result shows that we could detect up to the 200 ppm is the limit. Below 200 ppm, we cannot detect in the laboratory setting, and about 200 ppm, we could detect rare earth elements. And she applied this to a new airborne sensor called Everest-3, and there are these 3 different parts of the mine. This is the mine processing area and the tailings where we could see this. And you could see this in this animations. Let me see if this plays. Yeah, so this animation shows the best inside index and then put on a Google Earth. So different parts, this is the processing areas, mine, and different parts of the mine could brighten up with the with process images. So we could see this exactly where the rare earth elements are in the mine. So I think I'm going over time, but I think I'll just quickly show you now. So we showed you this example from an active mine where we know rare earth is mine and it's detecting. Can this be applied to areas where we don't know if there are minerals or rare earth minerals? So when we were processing this data for Mountain Pass, we always had this anomaly. We had this high bestness index in this area. So first we thought that was some noise, and we would keep on thinking about it till we read about it. And what we found that this is the Mountain Pass mine, rare earth mine, and this is the location. We found that in 80s and till 90s, there was this 14-mile long pipe that was taking fluids from the processing unit of the mine to these ponds here in this near this alluvial vein. And then we found this one report that federal government found that there were this many rupture of this pipes, and a lot of fluid was released into this dry lake area, this Ivanpa dry lake, or this alluvial vein systems. So we tried on this now, these different techniques. This is the spectra obtained from these different images, and we could see this dips that's associated with a neodymium. And here it is. The pipe was coming in this direction, and this is that location. See this here. This is Everest Next Generation. These are the 3 different indices that we applied. This is Everest Classic. This is Haisui data, that's Japanese side. This is DSIS. Here is the Hyperion data, that's the old one. And actually Hyperion, which was old, even shows brighter colors, meaning could be a lot more. And then even in emit, which is 60-meter, do show anomaly here. So this indicate that it is kind of very resistant to erosion also. All this time, it is still this rare earth detection being detected from this part of the desert. So currently what we are doing, this is Navajo coal mine in New Mexico, where we went. There are lots of reports that coals in Illinois and many other parts of the United States have higher concentration of rare earth. And I think some of the coal mines in China has like lot more, and even in Russia, rare earth element. And this is Parish plant. This is the southwest of Houston. This is in Rosenberg or Richmond, where they are burning coal. This is coal and that's being burned. So the idea here is that to see if we could detect rare earth elements in coals or fly ash obtained from coal. So here is some of this is ongoing research. Dr. Yagas is also part of this research with us. So we took some samples. This is the samples from Navajo coal, ash generated from a Navajo coal mine. And then we we applied this Besnaside index, or we applied this neodymium detection. And then we added some neodymium to samples, and we could see it very clearly, because coal is a very different medium to detect rare earth. So we are experimenting with that, and this is the coal ash sample that we obtained from Parish Power Plant, and we could see it very well. Now, the next step of this would be that we will be applying to some of the mines with higher rare earth elements, or potential higher rare earth elements, presence of higher rare earth elements. So I think what we just showed you here, that remote sensing in itself could be a very powerful tool for detection of some of those critical minerals using ground-based sensors, drone-based sensors, or even satellite-based sensors. And then the technique that we developed for rare earth, it's not only useful for active mines, but it could detect rare earth in areas that's unknown. And we also feel that integrating this remote sensing hyperspectral imaging with other data sets, say geophysical data, with this new AI techniques, may open up new ways that's not been even explored, and could be really useful for this discovery and expansion of critical minerals. With this, I think I'll stop here.